Welcome to the Mechatronics Revolution, Fundamentals and Core Concepts. In this lesson, we'll explore the mechatronics design process. The learning objectives of this lesson are to illustrate a functional block diagram of a typical mechatronic system. We'll enumerate the steps in the mechatronic system design process, and then we'll discuss and emphasize the need for analysis, modeling and simulation, and revision in the mechatronic design process. Let's revisit our three example robotic systems. As we can see, each of these devices is a highly integrated system of sensors, actuators, and microcontrollers or embedded computers. It's important to understand that when we build these devices, we go through a rigorous process of mechanical design, electrical design, and software design. And that allows us to build a relatively complex device like this inverted pendulum in such a way that it works reliably and effectively and performs according to the specifications that we've set for our device. What we can see here is a general system block diagram of a mechatronic device. This block diagram captures all of the main mechatronics components that we usually see. We can see we have an embedded computer or a microcontroller, which then provides a signal to a digital to analog converter. Maybe that signal is amplified or provided to a driver circuit, which then drives actuators. Those actuators control the movement of a mechanical device, some type of mechanical device. It could even be a fluid device, any kind of mechanical device we can think of. We then measure some outputs from that mechanical device using a sensor or multiple sensors. We take that sensor data, we put it through some type of signal conditioning. That signal can then be either digital or analog, so we may need to use an analog to digital conversion step to take that data back to the microcontroller. And of course, there's also a user interface where a user provides commands or inputs to that mechatronic system for how it should operate. Now, this general block diagram applies to pretty much any mechatronic system we can think of. We can also divide this block diagram into several components. Number one, the electrical components on the left, and number two, the mechanical components on the right of your screen. And throughout this course, we will talk in detail about each one of these blocks so that by the end, you'll be equipped with the knowledge you need to go through this mechatronic system design process to design whatever type of device you're interested in. Let's talk in detail about the mechatronics design process. Now, when you're designing a mechatronic device, it's critical to balance engineering analysis with hardware experimentation in an appropriate way. Many people try to design a mechatronic device using some type of trial and error method where they'll maybe build something, try it. If it doesn't work, they'll make some tweaks, test it again, and so on. The problem is that if you don't use a rigorous engineering analysis approach, then that can lead to, for instance, excessive development time. It can take a long time to get something to work. When you do get it to work, it may not work very well. And so you might not achieve the objectives that you've set for whatever you're trying to build. So it's important to balance both an engineering analysis process with a hardware experimentation process. Let's go through the steps in a mechatronics design process. The first step is to come up with a goal or set of requirements for your system. You want to answer questions like, what do I want the system to do? How well does it need to do it? And maybe we want to be quantitative about that and set numerical requirements on performance. Here's some examples of a goal of a particular system or particular requirements we might set. For instance, suppose we're designing a gate for a parking garage that goes up or down when a car is near it. And so the goal of that system would be to detect the proximity of a car and open the gate when the car nears the exit. Alternatively, for instance, if we're designing a printer, then maybe we want to say the printer has to print in color and it has to print 15 sheets per minute. Following that step, we then want to create a functional description of our system. We want to answer questions like, how does a system accomplish the goals? What types of sensors, actuators, computers, and user interfaces will our device use? And this is where we usually create a very detailed system block diagram where we illustrate and design the connections between our sensors, actuators, and computers, as well as user interfaces. For instance, with these two example systems, we might say that our parking garage gate uses an induction loop sensor to detect if a car is near, a servo motor to open the gate, and a microcontroller to do the relevant processing. Likewise, for our printer, we might specify the use of stepper motors, limit switches to detect where a print head is located, an actual print head to do the printing, and an embedded computer to control the device functionality. Step 3 is component specification and analysis. Here we want to pick out the actual components, the make and model of the components we want to use, whether that's a certain make and model of a motor, a certain embedded computer, microcontroller, certain sensors, or electronics components. We want to make sure that as we're picking components out, we pick out components with the appropriate specifications. So for instance, you may have heat dissipation requirements for your electronic components. You may have processing requirements for your computers. You may have torque requirements for your motors. And the way you arrive at those requirements is by using physical laws to determine, for instance, torque requirements, electrical calculations to determine heat dissipation, or other types of physical laws or analysis techniques to arrive at these specifications. And it's important to understand that sometimes modeling and simulation is a part of that process, and that's why there's a modeling and simulation block shown between steps 2 and 3 to allow us to pick components that will work for the device that we're building. Step 4 in this process is to, of course, obtain all of our components and then actually build the system. So here we'll fabricate the mechanical elements, we'll design and fabricate the circuit boards or electrical components, we'll write the embedded software. Step 5 is integrating all of these things together. Typically, we might go build a set of mechanical components, design and build our circuit boards or our prototyping boards, and then implement our software, but then we have to integrate them all together. And that's a step that's harder than it sounds. Oftentimes when you integrate a mechatronic device, you have to pay a lot of attention to more mundane details like where wires run. Do you have wires that are long enough to connect to things? Or will one part get in the way of another part? Things that are maybe difficult to design and understand until you get to the system integration step. Following system integration, we of course move to testing and inevitable troubleshooting of our device. Here, we'll do some limited testing of device functionality, making these tests more and more complicated until we finally get to full system performance testing. Now, when we're doing testing, we want to make sure that we record data from our device. We'll record that data using sensors that are on board the device that maybe it uses in normal functionality, and then we may attach extra sensors called diagnostic sensors on the device or near the device to take data that will help us during troubleshooting, as well as determining whether our system met the specifications that we set. Finally, there's an iterative loop here where after we test, we troubleshoot a little bit, we may find that we need to go revisit the functional description of how our device actually works. Or we may need to revisit the components we've picked because maybe the components didn't work like we thought they would. And this is that process of design revision that is so important for developing mechatronics devices. The mechatronics design process that I've just outlined is really important to follow, even for simple systems. Turns out it can save you a lot of time, money, and effort. If you just use a trial and error method, which is oftentimes used by beginners that like to get started in the mechatronics space, that may work for simple systems, but it will not work for more complex devices like, for instance, here's a Mars rover, or for instance, a drone or something like that. The trial and error methods when creating these systems turn out to be too costly. As a result, we want to leverage our engineering tools and as needed modeling and simulation in order to reduce time, reduce costs, and reduce risk when we build this device. To summarize what we've learned in this lesson, mechatronic devices are comprised of a collection of electrical, mechanical, and computational devices, and these are interfaced in a relatively consistent way across any mechatronics device. The mechatronics design process is an incremental step-by-step methodology. It incorporates rigorous engineering analysis and modeling and simulation throughout, and it allows us to maximize our probability of success. A rigorous design process, such as the one we've outlined here, should be employed for all mechatronics devices, regardless of complexity.